In this slide series, we're going to start moving beyond looking at measures of association, telling us whether, for example, two variables vary together, to start to look at trying to explain the behaviours of one variable using the predictive power of another. To do this, we're going to look at modelling data and the different approaches to modelling. So what do we mean by modelling data? Up to now we have looked at correlation, so that's measuring whether two or more variables vary together. What correlation doesn't do is actually imply causation, and nor does it actually explain the dependency of one variable on another. For example, a simple model exploring variations in cancer mortality by a proportion of GDP spent on health services can be expanded to include levels of education, and factors such as access to healthcare, age profile of the population, and gender. Models can be used in two ways: as a tool to explain and understand causality, so what are the variations in health screening take-ups, and also as a tool to predict, so what would the likely proportion increase in accessing health screening services be if GP practices were to offer increased clinical hours. Both of the models describe highlight the differences in the types of variables. So we're looking at independent variables or predictive variables. So for example, proportion of GDP spent on healthcare services or number of clinical hours. And the dependent variable, or what we call the outcome variable, or Y, is, say for example, cancer mortality or percentage access, health screening services, and those kind of things. The effect of different predictive variables can be assessed. When we model data, it's important to remember that no model is a perfect fit. It is probabilistic, consisting of the statistical model of the data to best fit, plus the remainder of that that did not fit, known as the error term. There are also a range of techniques available that are concerned with reducing dimensionality in the dataset, for example, identifying latent variables and grouping cases according to like characteristics. Now, there are a few key basic steps in modelling data. Having an understanding of your data, the variables and the relationships you wish to explore to executing any modelling technique is known as theory-driven modelling. For example, simply having a prior understanding of your independent or predictor or explanatory variable and distinguishing this from the dependent or the effect variable. That's what we think of when we think of theory-driven. The opposing approach is known as data-driven, and this is where data or variables are placed into a model without any prior knowledge at all. Such an approach should generally be avoided as it doesn't enable you to construct meaningful models. The use of modelling techniques requires a really good understanding of the data that you have collected at a descriptive level, and basic univariate and preliminary bivariate analysis should be undertaken. This is particularly important as each modelling technique has its own set of assumptions relating to the characteristics of the data placed in the model. Data that has extreme values or outliers or does not have a normal distribution of values may not be good candidates for inclusion in a model. Where these occur, transforming data can offer a very useful solution. Transformation techniques are varied, with the most common being logarithmic transformation. Modelling techniques, like other statistics, are dependent on the level of measurement or data type of your research data. In the social sciences, a combination of data types is usually very common. It's quite common, and there are data transformation techniques that are available to deal with these issues. Parsimonious models of the least complex providing maximum explanation are preferred. The basic steps that you need to undertake when modelling your data are enter the variables into your model, identifying the independent and dependent variables appropriately. Use the data to estimate the error or part of the data that cannot be explained by the model. Evaluate the model for its fit to the data. And the model that is built from the data can then be tested against the data to see how good the fit is. A model that has explanation of, say, 63% is much better than one of 31%, provided that the variables in the model actually make some sense. If using the model for prediction, values can be entered into the model to calculate predicted values. The following slides are an overview of the most frequently used modelling techniques at level 7. Now there are a number of different modelling techniques. We have your regression models, and those take the form of simple linear, multiple linear and binary logistic regression. We also have data reduction techniques. Those go in the forms of things like cluster analysis and factor analysis, and then we also have multi-level modelling. In this slide series we are going to have a look at simple regression. This is where we have one independent or predictive variable, and multiple regression, and this is where we have more than one independent or predictive variable. In the next slide series 6, we're going to have a look at an overview of binary logistical regression, data reduction techniques such as factor analysis and cluster analysis, and multi-level modelling. The techniques of factor analysis and cluster analysis are widely used in market research to identify latent variables and grouping cases to reduce the data dimensionality. In more recent years, social statisticians have developed multi-level modelling techniques to adjust for hierarchical relationships in data sets. These approaches focus on production statistical modelling that takes account of cases being nested within often naturally occurring groups. For example, when accessing education attainment levels of children, the individual cases or the child are nested into class groups that are organised into cohorts within schools, within local education authorities. So to start with, we're going to have a look at simple linear regression. Now, linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. One variable is considered to be an explanatory variable, and the other is considered to be a dependent variable. Linear regression uses scale data for the independent and dependent variable. Categorical variables can be introduced providing that dummy variables are created, and we're going to talk about that in a moment. But essentially, linear regression extends Pearson's R correlation coefficient, or sort of moves it on. So we use linear regression to estimate the unknown effect of changing one variable over another. And you can see here that linear regression line has an equation in the form of y equals a plus b times x plus e. Y is the dependent variable, x is the independent variable. A is our intercept, which is the point at which the line of best fit will cross the vertical y-axis, and b is the slope of the line, which is the rate of change in y for a change in x, and e is the error term in the model. Now, when running a regression, we're making two assumptions. The first assumption is that there is actually a linear relationship between the two variables, i.e. between x and y, and that this relationship is additive. Technically, linear regression actually estimates how much y changes when x changes by 1 unit. Now, the most common method for fitting a regression line to the observed data is the method of ordinary least squares, or OLS. The goal of linear regression is to adjust the values of the slope and intercept to find the line that best predicts y and y from x. More precisely, OLS calculates the best fitting line for the observed data by minimizing the sum of the squares of the vertical deviations from each data point to the line. If a data point that has been observed fits exactly on the line, its vertical deviation will of course be 0. Because the deviations are first squared, then summed, there are no cancellations between positive and negative values, and you can think of it then in the same way as deviations around the mean, but this time we're looking at deviations around the regression line instead. While some data points will fall on the OLS regression line, not all will. Some will be close to the line and others may be further away. Those points that are further away are known as outliers, and depending on their location, they may have a major impact on the regression line. They may represent erroneous data or may indicate a poorly fitting regression line. The difference between the observed data point and the regression line is the error or residual. The error is the bit that cannot be explained by the formula for the regression line. We rewrite the formula to include the error term, and you can see the formula as it's written on the slide here. Here we have y, which is the continuous dependent variable or the prediction. X is the continuous independent variable, so the one that you're using to predict y. Alpha is the intercept value for y when x equals 0. And beta is the slope, this sort of regression coefficient on x. It tells you how much the value of y changes when x increases by 1 unit. And the error term, so the term at the very end, that represents all other factors that have an effect on y other than x that we cannot take account of. So they're the sort of known or unknown factors that we cannot take account of. Now, we don't know alpha and beta in our population, so we need to estimate them based on our sample data. If we remember back to a sample mean and calculating confidence intervals, we use those to access the range of values in which the true population mean will fall. Now, SPSS or any other statistical package will actually calculate them using the sample data. Of course, these estimates are subject to sampling variability, and the confidence intervals will also be calculated for alpha and beta. And using the t-statistic, we can actually test the null hypothesis for the regression coefficients to assess if the coefficients are significant or not. Here's an example of a scatter plot with a linear regression line plotted. Here we can see that the dependent variable is life expectancy and the independent variable is literacy. The data set used is from the World Bank data sources on country level statistics. The model is exploring the association and relationship between literacy rates and life expectancy, with the researcher interested in seeing if there's a positive correlation between the two variables, whereby increasing literacy, which is used as a proxy for education, improves life expectancy through, for example, life changes, so improving employment, income, health, outcomes, and so on and so forth. So it's basically that improved education levels bring improvements to both individuals and to the wider economy of the country. The regression line is shown. Okay, on the line in here we have alpha of 33.423. Which is the constant or the intercept, and we have beta of 0.394, which is the slope for the independent variable literacy. Plugging those figures in, we get an r-squared value of 0.4363, and this means that literacy rates explain 43.6% of the variation in life expectancy in the model, i.e. 56.4% of the variation in life expectancy is not explained by literacy levels. Now, r-squared is the measure of goodness of fit for our linear regression. The r-squared equation is essentially a ratio of the variance broken down into two parts. The first part is the proportion of variance that cannot be explained, and the second part is the proportion that can be explained by the relationship between x and y. If you think of r-squared as the fraction of total variance of y that is explained by the variation in x, the value of r-squared will lie somewhere between 0 and 1. An r-squared value of 0 means that there's absolutely no linear relationship, and as you can see in the top left hand diagram, it's a completely horizontal line, and the horizontal line is sort of going through the mean of all y values. When r-squared equals 1, so in the bottommost picture, we can see that all points lie exactly on a straight line with no scatter, so that means there is an absolutely perfect correlation between x and y. Now, this slide shows what a regression analysis would look like in a statistical package such as SPSS. We can see here, we can see the significance levels. okay, for the beta coefficient, okay, and for the alpha coefficient. And we can have a look at things like the confidence intervals, so the lower and upper boundaries, okay, for both the alpha and beta intervals. Now, our hypothesis testing for alpha and beta, our null hypothesis is that either beta equals 0 or alpha equals 0, and the alternative is beta does not equal 0 and alpha does not equal 0. Now, we can see that when we look at our t-value, okay, we can see that it is less than 0.05, therefore we can reject HO for alpha, and we can also reject HO for beta as well. Now, with simple linear regression, there are of course a number of assumptions that we have to think about, and there are 5 assumptions. The first one is that that in the population there is a linear relationship between x and y. The second one is that for every value of x, values of y are normally distributed. The third is that the variance of x is constant for all values of x. And for 4, the observed values of y are independent of each other. And the last one is that accurate measurement is that things must be accurately measured and there must be accurate data collection. Now, these assumptions can be checked using a variety of residual plots available in statistical analysis packages. So, multiple linear regression. Multiple linear regression is essentially an extension of simple linear regression. This is where we have 3 or more variables in the equation. We have one outcome variable, our dependent or y variable. We have 2 or more predictor or x variables, our independent variables. They're used to explain the variation in the y variable. The y variable must be scale or continuous data, and the x variable should be scale or continuous data, or where variables are categorical and we have to use dummy variables. The technique is available in many different statistical packages and specialist software, from SPSS to Stata and so on. Now, multiple linear regression is expressed in the same way as simple linear regression, except we've just got as many beta x combinations as we want. Okay, so where we have alpha, then we have beta 1, beta 2, beta 3, depending on how many different independent variables we're going to be looking at. The purpose of multiple linear regression techniques is to find the model of best fit. Now, the coefficients are only appropriate for particular models, and we start by assessing the individual coefficients for y and x, for y and each x within the model. Now, there are 3 main methods for actually entering variables into a model, and they can be specified in different software packages. We have just entering the variables, we have backwards elimination, and we have stepwise as well. So with enter, basically all variables are entered simultaneously into the model. With backwards elimination, all independent variables are initially entered, and then non-significant variables are removed once at a time. With stepwise, the starting point is the fitting of the most significant variable, followed by the next most significant, and so on. Each variable is entered and is assessed in the model, and if it is subsequently found to be not significant, it is then removed from the model. So let's have a look at an example of multiple linear regression. In this example, we're going to see how literacy and GDP affect life expectancy. Just a note on GDP, here we have actually used the log of GDP, as GDP is typically not normally distributed, and so we have to do a log transformation to help correct this. But as you can see here, we have a life expectancy, then we are working with our two variables, okay, our 2 beta variables. So B1 we're dealing with literacy, and B2 we're dealing with the log of GDP. Now, this is the kind of thing that you would expect to see once you'd put your multiple linear regression in, and you'd pressed all the correct buttons in something like SPSS or Starter, you would come out with this kind of table. And here you're going to have your B values. So if you look at your B value column, this gives you your beta values, okay, and they reflect the relative scale and measures of each predictive variable. So you can see we have our literacy and our GDP log. We then have the standard error. We then have a look at our beta values. So standardized allow you to compare the relative importance of each of the predictive variables within the model. So you can see our beta value of 0.3 and our GDP log value of 0.511. And we automatically run a t-test on that. Okay, so our t-test on that with our null hypothesis, which is testing for a value of beta equaling 0. If our p-value that we gain from our t-test is greater than 0.05, then we remove the variable from the model. If our p-value that we gain from looking at that score is less than 0.05, then the variable has a significant influence on the dependent variable, so we keep it in. So if we actually plug that into equation, we have life expectancy equals our alpha, so our constant, which is 21.819, so you can see that under the B column, that's our constant, and then we add our B1, our beta 1 value, okay, which is 0.175 times literacy, plus our B2 value, our beta 2 value, which is 3.663 times GDP. Now the overall fit of that model, once we've done those various different calculations, let's actually examine what the output from the regression analysis is going to be. Now from that example, we actually get an R-squared value of 0.560. As with simple linear regression, this is actually the sort of the proportion of variance that is explained by the model. So this means that the variables in our model, literacy rates and GDP, explain 56% of the variation in life expectancy in this model. Conversely, it also says then that 44% of the variation in life expectancy is not explained by the variables in our model. As with simple linear regression, we have a look at the p-value of the f-test, okay, to see if the overall model is significant. The p-value answers the question, if there were no linear relationship between x and y overall, what is the probability that randomly selected points would result in a regression line as far from the horizontal than you observed? The p-value is calculated from an f-test. A statistical package such as SPSS will calculate your f-statistic and give you your 2 degrees of freedom. So your numerator and your denominator degrees of freedom, which is your in-between group numerator and your within group denominator. With these you can look up your f-test critical value in a statistical table. In our case, the f-test gives a value of 56.539 with 2 and 89 degrees of freedom at p-level 0.05. Looking this up gives us an f-test critical value of 3.15. Our f-test statistic is far larger than the f-test critical value, so we reject the null hypothesis and conclude that there is a linear relationship with at least one of the predictive variables in the population. Now what the f-statistic does not tell you is which of the effects are significant. It only actually tells you that one of them are. As with simple linear regression, the assumptions of normality can be checked if we use a variety of residual plots that are available in statistical packages. Now we've talked a little bit about dummy variables as we've gone along. So generally when we're dealing with linear regression, we are dealing with data that is scale or continuous in form. We can use other forms of data, but we have to use dummy variables. Now that allows us to actually sort of enter categorical level data into a regression model. It basically involves reclassifying an original categorical variable into two or more dummy variables with either a 0 or a 1. The number of dummy variables required is always the number of categories in the original variable minus 1. So we can have a look here. Here's an example. Okay, so the original categorical variable was which area of England do you live in, north, central or south, and we reformat that to north equaling 1 or 0 if it's north or other, central 1 or 0 if it's central or other, and south 1 if it's south and 2 if it's other. So that basically enables us to input that into a model. So to enter dummy variables, we enter them individually into a regression model. So if we look at this example, looking at unemployment rates and how literacy rates and the area in which somebody lives affects their unemployment rate. We've got the unemployment rate being our y variable, we've got x1 being our literacy rate, and x2 being our area of the country, north, south and central. Dummy variables are created for x2, where we have Z1 north, Z2 south, and Z3 central, and we include them in our model that way.